Methanol has a variety of different hydrogen-heavy atom bonds. We have hydrogen attached to carbon or hydrogen attached to oxygen. Which one of these is more acidic, do you think? If you're not sure, look at the last slides that we were working on. If you were to compare a carbon-hydrogen bond or an oxygen-hydrogen bond. One of these is significantly different in acidities. Carbon-hydrogen bond is about pKa 48. Oxygen-hydrogen bond in water was about 15.7, but for us, the pKa of this particular bond is 16. This is close enough for our memory. Draw carboxylic acid. Carboxylic acid was a group that we talked about in video. It has two different types of hydrogens. It has hydrogen attached to carbon or hydrogen attached to oxygen. These two look quite similar to one another. But carboxylic acid, the presence of this carbonyl group, we'll talk about this more later, changes the acidity of this drastically. It drops to pKa of 4.75. You might not think that 16 and 4.75 are very different from one another. Well, that's okay. But pKa, if you'll recall from where the number came from, it's a negative logarithmic value. It's not the case that acetic acid is about 3 or 4 times more acidic than an alcohol. That's what it looks like from these numbers. These are negative exponential numbers. This is 16 zeros, and this is 10 to the 4 zeros difference. The difference in acidity to these is 1 times 10 to the 12th, because these are exponential units. So to say that acetic acid is a little more acidic than methanol is completely fake and false. These are drastically different in acidities, and it's not easily reflected in these, but these are negative logarithmic units. Maybe it's 11 or 11 or 12 zeros more time acidic than this. If we're actually to write out the Ka's for these particular compounds, which is the strength of this bond and how easily it gives up a proton, we'll see that this has 10 or 11 more zeros after it in this one. So these pKa values, this is drastically more acidic than that. I want you to put to memory that a carboxylic is 4.75. HCl has a negative, kind of difficult to actually measure this in the real world, but -7 is roughly where we'll put HCl. You know that it's a strong acid from general chemistry. It completely dissociates in water is what a strong acid means by definition. HCl is the definition of it, completely dissociates. The smaller this number, the more acidic it is. And finally, the last functional group that I want us to actually put to memory we're going to take a ketone here, and this molecule is called acetone. And there's only one type of hydrogen bond in it. It's to carbon. This particular molecule, the pK is 19.2. This is actually quite different than methane. Methane, we said, was 48. And this is a carbon-hydrogen bond. Looks very similar to the carbon-hydrogen bonds here. But this carbonyl group is going to play an important role between these two types of compounds. They're not similar anymore when it comes to acidity. This is kind of similar to what's happening here. We have an OH group. This is much closer to water. Water's 15.7, 15.8. This is 16. Very, very close in acidity. We have an alcohol group again, but it's attached to a carbonyl, and we know that the name of this functional group is carboxylic acid. The acidity changes quite drastically, remarkably. It increases by 11-fold, 10 or 11 zeros. 10 to the 11, 10 to the 12, somewhere around here, that many zeros. The difference between these two is something like 1 times 10 to the 28. The difference between these two particular species here. It's not that it's twice as acidic or half as much, so this must be twice as acidic. It's 10 to the difference between the number of zeros between these two negative logarithmic units. So the carbonyl group plays an important point, an important role. We'll see that in our video for tomorrow's lecture. What we're going to do now is use these pKa values and do a few problems together, put them in our notes, and see how pKa's can be used to predict the equilibrium of a reaction. From our first slide together today, we had just this simple acid-base reaction between water and sulfuric acid. Make sulfate and hydronium ion. And we said this was an equilibrium reaction, and we didn't really talk about it more than that. Equilibrium reactions are quite fascinating, very difficult to understand on some level. Which way does this favor at equilibrium? Well, that's the type of question that pK lets us solve very, very rapidly. If we simply know which species are stronger acids, which species are weaker acids, we'll be able to make some predictions. So we're going to use some of these pK values that I've just put in our notes that you're supposed to memorize. And we'll talk now about acid, base, equilibria. We're going to put up some new species here. We'll use HF as our acid. We should know right away that this is an acid. And the species we'll put next to it, we're going to put up a compound called sodium acetate. This particular compound's name is sodium acetate. It's okay if you don't memorize it. I'm not going to ask you very complex nomenclature questions ever again, but this particular compound, sodium acetate, if we look very carefully at it, it's the conjugate base of a carboxylic acid. So when we look at these two particular things, this is our acid, this is our base. How did I know that? Well, I have lots more experience than you, so it's okay, but how should you figure this out? Well, this particular compound you should already recognize as an acid. We've used it as an acid many times before. It looks like HCl, a compound that you do know. It's very similar to HCl. This particular compound, maybe you don't know too much about it, but one clue that it might be a base is that it has a negative charge in it and lots of electrons. Okay, looks a little bit like sodium hydroxide. So you'll see some similarities as we move along, okay? But for now, if you could pick out that this was the strong acid, great. This will then become the base. If you couldn't pick it out, then keep practicing and you will. So if we identify these two things as acids and bases, we're going to use the Bronsted-Lowry definition. One of these things donates a proton. One of these things has lots of electrons. It can accept a proton. Why don't we look at the polarization of this particular bond? This is a polar bond. There's this direction. You know, there's partial plus charge on this hydrogen, partial minus charge on that fluorine. These two things are going to react. I want you to use a mechanistic arrow and practice the things that we've done in the first half of our lecture today. I want you to use arrow pushing activity and exercise. You're going to use two arrows, okay? One of them's going to start from the base. Where is it going to go? It's going to go to the acid somewhere. We're going to form a new bond. A second arrow is used because something happens when this interacts with the acid. First, we form a new bond, and then something else happens. Do you remember what happens? Try and draw arrows from here to where you think it should go here. And then if there's a second arrow in this particular molecule that you need to draw based on what we practiced in the last hour and a half together, do that. And then finally, draw the resulting two products over here. Okay? So this is an equilibrium reaction. I want you to practice on your own, drawing the mechanistic arrows between base and acid. I want you to draw the conjugate bases, conjugate acids. I want you to put in all the formal charge. This is a moment, 60 seconds. Please draw in as best you can what you think should be over here, what you think the arrows look like for here. Do your best. Some of you should have great success with this. Others of you should have moderate success with it. But you shouldn't be sitting there with nothing to do unless you've been sleeping for the last hour we've been together. This is a chance for you to practice what we've been doing right now in real time, and then I'm going to show you the answer, and you'll be able to evaluate if you're keeping up, if you're internalizing things, or if this is going to be challenging for you and you need to put time into it. Okay? Any scenario is okay for me, but it's important that you can recognize where you are. This is that chance. I'm going to start drawing arrows the way I think they should be. I'll talk about it later, so if you keep working on your own, that's absolutely fine. What I'm hopeful is when you saw these labeled as acid and base, if you knew that already, great. If you just followed my lead that this is base and this is acid, I'm hopeful that you took the initiative and took these electrons, a pair of electrons, and drew them to form a new bond with this hydrogen. We did this about 4 or 5 times already today. You go back in your notes, there's the proof. When we form a new oxygen-hydrogen bond, hydrogen doesn't want 2 bonds. The weakest bond breaks and it goes to the electronegative atom. If we draw the result of this, it should be the conjugate base, F-. So if you had trouble with these arrows, you should have at least been able to draw F- as the conjugate base of this. I told you this was the base in red. You should be able to draw its conjugate acid, even if you can't draw the arrows. My hope is, and my goal for you is, that you get to the point where you can draw the arrows to get to these 2 particular species. Now what we're going to do is we're going to evaluate carefully the equilibrium. Does the equilibrium favor the products, or does the equilibrium favor the reactants?